So good morning, everybody. I hope you were able to get some rest and are ready to finish off the week strong. Continuing today on our discussions of heat exchangers. Today we're going to be talking about shell and tubes. For the majority of the class, if we have time, we'll start discussing another method for analyzing heat exchanger performance. So without further ado, go ahead and kick it over the notes and start the lecture for the day. So from last time in our discussion of heat exchangers, we have been taking a look at the design equation for heat exchangers, which states that the heat transfer rate in a heat exchanger can be calculated by knowing the overall heat transfer coefficient U, the surface area of the heat exchanger, the corrective factor for the delta mean, log mean temperature driving force, or delta T log mean. And last time on Wednesday, we talked about calculating U as a function of mainly the inside and outside heat transfer coefficient. And so what we say is the inside heat transfer coefficient we call the tube side heat transfer coefficient, and HO would be the shell side if we're talking about a shell and tube heat exchanger. And F, we had already discussed, being a function of two values, a Z value and an eta value, where Z looks at the relative driving force between the hot side and the cold side, and eta looks at the relative values between the cold side and the hot side. And typically you can use the big F expression, or you can rely on some correction charts. So that was what we spent a majority of time on Wednesday. Today we're going to talk a little bit more in terms of shell and tube heat exchangers, and particularly calculating heat transfer coefficients.
Can I ask a quick question on the Z and the NH?
Sure.
Is that just for countercurrent flow, or is it also for parallel flow?
For co-current?
Or co-current?
It's really, F is technically for multi-pass exchangers.
Okay.
If you have true countercurrent flow, F is going to be approximately 1. But if you have a multi-pass exchanger where you're going to have parts with cross flow, that's really where F is going to come in. And for the majority of heat exchangers, there's always going to be some degree of cross flow. Unless you're looking at really basic double pipe heat exchangers, which you're probably not going to use for, large heat transfer systems. Good question. All right, so we're going to look at calculating heat transfer coefficients for a shell and tube heat exchanger. And so when we're looking at the tube side, we're typically counting H sub I, or the inside heat transfer coefficient. In here, we can apply our principles of internal force convection. Meaning, if we have fully developed turbulent flow, it's a little early to start this computer. which equation can we rely on?
Is it the Colburn equation?
It is the Colburn equation. Thank you, Nick. All right, so Nusselt is going to be HL sub C, or in this case, the inner diameter of the tube over the thermal conductivity of the fluid, which equals 0.023 times Reynolds to the 0.8 times Prandtl to the n. And if you're designing your heat exchanger right, you should be in turbulent flow. Now, for the shell side here, I'm trying to make it so you can see both. The flow is more complex. And to kind of explain why, let's take a look at the diagram of a shell and tube heat exchanger that we have. Let's just look at the one on the top. So in this simple heat exchanger, if we're looking at the shell side fluid, we see the fluid, depending on direction, we'll say it's going here. It would flow if it's going from the bottom up in this type of arrangement. And so it's done that way, one, to make sure there's good turbulent flow, as well as good contact between the shell fluid and the tubes. But at the same time, if we're characterizing how that fluid flows, we see a couple things. Flow that kind of goes over the tubes and flow that goes with the tubes. And so explaining how this complex flow pattern influences our heat transfer coefficient requires a couple different things. And the more complex thing that we look at is how this influences the flow area as well as the mass velocity. And so if we look at the equations that describe the shell side heat transfer coefficient, what we rely on is an equation known as the Donahue equation. And the Donahue equation, well, it does describe the heat transfer similar to the Colburn equation. There's some key differences. Which I'll explain here in a second. And so we see kind of the similar form of the Colburn equation, right? We have a constant times Reynolds to a power, Prandtl to a power. We also have this viscosity correction when the temperature of the fluid and the temperature on the pipe surface differences such that we see a dramatic shift in the viscosity. We can have a small correction factor for that. But what we find is that while our Prandtl number doesn't really change much, Cp mu over K, our Reynolds number is described instead of as a density times velocity, we use what's known as an effective mass velocity, where G sub E is equal to the square root of two different mass velocities, a G sub C and a G sub B. And so the question becomes, well, how do we calculate these two mass velocities? Well, G sub C is calculated by taking the mass flow rate defined over a particular area. G sub B is the same mass flow rate over a different area. And these area essentially describe the flow area for the fluid in the shell by looking at different areas or points of fluid flow within the shell of a shell and tube heat exchanger. And so, looking first at S sub B, we can calculate S sub B, this area, as F sub B times pi times D sub S squared over 4 minus N sub B times pi D sub 0 over 4, where F sub B is the fraction of the cross-sectional area occupied by a baffle window Let me clean that up. D sub S is the shell diameter. N sub B is the number of tubes in the baffle window.
When you say number of tubes in the baffle window, does that mean the number of tubes that flow through the baffle or the number of tubes that flow through the open space?
The number of tubes in the baffle window would be the number of tubes that are occupied by a particular section cut off by baffles.
Okay, thank you.
And so we typically calculate this as F sub B times the total number of tubes. And then D sub 0 is the outside tube diameter. And so S sub B is characterized as the air flow area in a baffle window. And so if we're looking at this in this diagram, going back, the area that we're describing, I should probably put it in pen mode. Come on. Pen mode, let's do this. S sub B is describing this flow area, right? So if you take the mass flow rate over this cross-sectional area, we're looking at that mass velocity. And that differs from S sub C, which if we see flow here, S sub C would be described here. So it's the flow in this transverse direction around the tubes, right? So we have two different types of flow this way and flow this way, which means we're going to have two different effective mass velocities. And so we have to find a mean for those velocities to determine our effective Reynolds number. So S sub C, it's a little more straightforward. It's P times d sub s over 1 minus d0 times little p, where big P is our baffle pitch. D sub s, once again, is our shell diameter. D sub 0 is the outside tube diameter. And little p is our tube pitch. Any more questions? I know this is a little odd.
When you say outside tube diameter, is that like the diameter of the tubes running through the heat exchanger?
Yes.
Okay.
But since the fluid in the shell sees the outside of the tubes, we're looking at it in terms of the outside diameter. This differs from the tube side, where the fluid in the tubes sees the inside diameter.
Got it.
Yep. And so this is the flow area. It's easier to say transverse flow area. And so if we're looking at calculating the shell side heat transfer coefficient for a shell and tube heat exchanger, you would have to identify these two flow areas, calculate the mass velocities G sub C and G sub B, find the effective mass velocity, and with that you can then calculate your effective Reynolds number. With the Prandtl number you can then calculate Nusselt, and then with Nusselt you can find your outside or shell side heat transfer coefficient. And if you were looking at finding an overall heat transfer coefficient, you would then have to calculate the Reynolds number and Prandtl number for the tube side flow, find its Nusselt number using the Colburn equation, then find the inside heat transfer coefficient, and then finally with the inside and outside heat transfer coefficient, you could then find the overall heat transfer coefficient for the shell and tube exchanger. So it wouldn't hurt to make yourself a little flow chart or step-by-step guide on solving for the overall heat transfer coefficient of a shell and tube heat exchanger. So let's take a look at an example. So in this exchanger, we have a tubular exchanger with a 35-inch shell that contains 828 3/4-inch tubes that are 12 feet long on a 1-inch square pitch. That's the tube pitch. If standard 25% baffles are spaced 12 inches apart, which is the baffle pitch, what is the shell side heat transfer coefficient, given that we have liquid benzene in the shell flowing at 60 degrees Fahrenheit at a mass flow rate of approximately 100,000 pounds per hour? And for this problem, we assume that the surface temperature of the tubes are 140 degrees Fahrenheit.
Is that saying the tubes have a 1 inch pitch or 1 square inch pitch?
Yep, a 1 inch pitch. All right. So let's take a look at doing this example. Calculating. All right, so we're looking at the shell side heat transfer coefficient, which means our Nusselt is given as HO K over D sub 0. Oops, I wrote that wrong. That makes more sense. Times 0.2, Reynolds to the 0.6, Prandtl to the 0.33, and viscosities, which I can clean up, to the 0.14. For this problem, Reynolds, that's provided, is D no, G sub E over mu. And so one of the things we need to find first is G sub E. The effective mass velocity is the square root of the two different mass velocities that describe flow in the shell side. So if you want, let's calculate those areas. Let's start with SC is equal to P times D sub S, which is 1 minus D0 over little p. For this problem, the baffle pitch was 12 inches or 1 foot. The shell side diameter given was 35 inches, which should be approximately 2.91 or 2.92 feet. The outer diameter is a 3/4 inch tube, so 0.75 divided by 12 or 0.0417 feet. And the tube pitch was 1 inch or 1 divided by 12 feet or 0.083 feet. With this information in hand, we can now calculate the transverse flow area, or we have 1 foot times 2.92 feet times the quantity, 1 minus 0.0417 feet divided by 0.083 feet. Hold on. I think I made a math error. I did. This didn't sound right. This should actually be 0.0625. That sounds right. So with that, our cross flow area is about 0.73 square feet. So we have one of the areas. Next, we need to find the second area, S sub B. S sub B is equal to FB times pi ds squared over 4 minus N sub B times pi d sub 0 squared over 4. For this problem, with the 25% baffle cut, F sub B is about 0.1955, which means N sub B is equal to 828 times 0.1955. So we get about 162 tubes. which means S sub B is equal to 0.1955 times pi 2.92 feet squared over 4 minus 162 times pi times 0.0625 feet squared over 4. Or S sub B should be approximately 0.81 square feet. So with this in mind, we can now solve for our effective mass velocities. G sub C is equal to 100,000 pounds per hour, or 1 hour, 3,600 seconds, divided by 0.73
Hey, Dr.
square
Lopez.
feet. Yes.
I'm sorry, but where did you get the value of FB from? I don't think I caught that.
It's typically something you would have to look up. For this problem, I just have that value. So it's
Would
a
you-
correlation between the percentage of the baffle spacing or the baffle cut as it relates to the actual baffle window.
Okay.
So if it was a homework problem, I'd probably just give it to you. But it's not something that you actually can calculate, unfortunately. But that's a good question. It's a fair question, definitely. So this area, our mass velocity is about 38.1 pounds per feet squared second. G sub B is 100,000 pounds per hour, where 1 hour is 3,600 seconds. Then area 0.81. So you got about 34.3 pounds per feet squared second. Which means with these two mass velocities, we can solve for our effective mass velocity as the square root of 38.1 times 34.3 or 36.1 pounds per feet squared second. Now, we do all this just so we can find our Reynolds number. So Reynolds number is equal to d sub naught outside diameter, this effective mass velocity over the viscosity. For this problem, the viscosity at, 60 degrees is about 0.7 centipoise. Which means we have 0.0625 feet times G sub E, which we just calculated as 36.1 pounds per foot squared second, divided by 0.7 centipoise, and 1 centipoise is 6.72 pounds per foot second. Oh, that's way wrong. I forgot times 10 to the minus 4. So this gives us a Reynolds number of about 4,800. Now with this, we can calculate our Prandtl number, which is the heat capacity, viscosity, divided by our thermal conductivity, which means we need to look up C sub P and K. For this problem, C sub P is about 0.41 BTUs per pound degree F, and K is 0.092 BTUs per hour foot degree F. Which means, solving for our Prandtl number, we put in these values, or 0.41 BTUs per pound degree F times our viscosity, 0.7 centipoise, times 6.72 pounds per foot second, divided by our heat capacity of 0.092 BTUs per hour foot degree F. Don't know why it's bleeding. I'll zoom in to make it a little neater.
I think you forgot the times 10 to the negative fourth again.
I did, thank you. These dang exponents. And I have to do a conversion because I've got seconds on the numerator, hours in the denominator. I've got space in the denominator, so I'll do it there. 1 hour is 3,600 seconds. Always make sure, because these values should be unitless, which means the Prandtl number is about 7.55. All right, so we did all that, and we finally have our Reynolds number and our Prandtl. Now we can calculate our Nusselt. 0.2 times 4,800 to the 0.6 times 7.55 to the 0.33. And seeing how we have a pretty good temperature gradient, we can do the viscosity correction. Viscosity of benzene at 140 falls to 0.38 centipoise. So we just put 0.7 over 0.38 to the 0.14. So we do that. And we do all these calculations. Let's see what we get. We get our Nusselt of about 68.6. So a lot of work for the Nusselt. But now we have our Nusselt, Hg naught over K, which means our heat transfer coefficient is equal to our Nusselt, or 68.6, times K, which we found as 0.092 BTUs per hour foot degree Fahrenheit, divided by our outer diameter of 0.0625 feet. which is about 101.1 BTUs per hour, feet squared, degree Fahrenheit. And if this was a shell and tube heat exchanger, we'd be like, great job, you're halfway there. Hopefully you guys were able to follow the process. It's not terribly difficult, it's just calculation intensive. But you can kind of see the steps of solving for that outside heat transfer coefficient. You need to identify the two areas, calculate your two mass velocities, find your effective mass velocity. With that, you can then calculate Reynolds, Prandtl, your Nusselt number, and finally your outside heat transfer coefficient. Any questions or points of clarification that I can make for this problem? All right, if not, let's have a brief discussion on a couple points that I like to make for shell and tubes, particularly when it comes to your choice of tube side / shell side fluid. Which are really just rules of thumb when it comes to shell and tube operation. So, if I had a corrosive fluid, should this be shell side or tube side?
Tube side,
Why?
because the corrosive fluid will only corrode the tubes on the tube side, whereas if it's on the shell side, it'll corrode both the shells and the tube.
That's close. You're like 90% there. I'll give it to you. You are correct in that you would definitely want this tube side. Primarily, if it's a corrosive fluid, you would have to probably use a special material of construction, so some sort of plating or lining in your system to avoid corrosion. And if you put it in the tube side, you only have to have that particular lining in your tubes as well as at the inlet. But if you put it in the shell side, you have to have that special coating or lining in both the shell as well as the outside of the tubes. What about if you had fluids that are primarily same, but you had one that had a much higher velocity or flow rate? Would you put that in the shell side or the tube side?
Would you do tube side because you'd have a like higher heat transfer and you wouldn't want it like going out of the heat exchanger?
Yes. Very good. And the easiest way to describe this mathematically is when we're looking at our heat transfer coefficients, right? The inside heat transfer coefficient is a function of Reynolds to the 0.8. And the outside heat transfer coefficient is a function of Reynolds to the 0.6, which means in general, we get a greater benefit of having the high velocity fluid on the inside or tube side in our heat exchanger. Because the higher the Reynolds, the higher the heat transfer coefficient, and the higher the heat transfer coefficient, the higher the overall heat transfer coefficient. And so you'll see a better benefit of having this fluid tube side. What about a fluid that's at a high pressure?
Tube side,
Why tube side?
because then you only have to reinforce the tubes rather than the shell and tubes to
That's
keep
true.
costs down.
You guys are on point today. Right? Less expensive than a specially designed. And the last one, if you had a fluid with a high viscosity, would that be shell side or tube side?
Would it be shell side since that would lower your Reynolds number? So kind of the same reasoning as our higher velocity on the tube side. Just like the opposite.
Yeah, very good. You guys get 20 points to the house of your choice. Yeah, so with a high viscosity fluid, you run the risk of laminar flow. And so operating at the shell side allows inherent turbulence. I know I spelled inherent wrong. Source, now I have to Google it. I have to know words good. Which avoids laminar flow. Because if we have laminar flow, we're going to have pretty low heat transfer coefficients. And so if you have a high viscosity fluid, you're essentially relying on flowing around the tubes, around the baffles to kind of give you the turbulence that you need for a good heat transfer. So these are the kind of rules of thumb. So I'm glad you found all of those intuitive. That's good. All right, we have a little bit of time. So we can talk a little bit about our next point of discussion, which is a different way to look at heat exchangers and their operation. This is through, instead of looking at the design equation, what's known as the Epsilon NTU method for heat exchangers. And this is used to analyze heat exchangers what's the best way to say this? Heat exchangers that you're not designing to build or buy. This is a heat exchanger that you have already, and you're trying to determine whether you should put it in service. So I'll say used to analyze heat exchangers to determine whether to put into service. What I mean by that is when you're looking at the design equation, 9 times out of 10, you're trying to find what's the necessary heat transfer area or size and cost of a heat exchanger to perform some heat transfer that you need for your process. When you're looking at the NTU method, you're saying, I have a heat exchanger already in existence, and I need to know if I put 2 process streams, let's say, in the system, one on the tube side, one on the shell side, what should I expect in terms of heat transfer rate, the efficiency, as well as the outlet temperatures after it runs through this exchanger. And so, the area is largely determined, and you can usually estimate the overall heat transfer coefficient. And so you're analyzing the system in terms of what's known as NTUs, or heat transfer coefficient, heat transfer units, excuse me. And so we can calculate the NTUs, or the number of heat transfer units, as the overall heat transfer coefficient times the area divided by the mass flow rate and heat capacity that exists in the shell and tube heat exchanger at a minimum. And what I mean by that is if you calculate, let's say, the mass flow rate of the hot side times the heat capacity of the hot, and the mass flow rate of the cold side times the heat capacity of the cold side, whichever value is the lowest, that becomes the minimum value. Whatever value is the highest is considered the maximum value. And so you're essentially looking at a comparison of the two fluids you have in your system and their ability to transfer heat between each other. And so by looking at the number of heat transfer units available and comparing it to the effectiveness ratio, R, which is simply looking at the MCP min over the MCP max, you can estimate the outlet temperatures of your heat exchanger. And you can also consider it in terms of the eta value, or the effectiveness value, which is TC out over TCN over THN minus TCN. And so you're looking essentially at the number of heat transfer units, the effectiveness of your heat exchanger, and the, R is the capacity ratio. And A is the heat exchanger effectiveness. And so with these three values, you can estimate these outlet temperatures of your heat exchanger. So I think we're about out of time. This is probably a good place to stop. So I think on Monday, we'll pick up here one more time. I'll go over this, the eta, epsilon, NTU method one more time. And I think we can work one or two more examples on heat exchangers. So let me go ahead and stop here. Is there any questions when it comes to the shell side heat transfer coefficients, or even this method? I know I just kind of touched on it briefly. All right, if not, I'll go ahead and let you guys go. Thank you guys so much for your attention. I hope you guys have a great rest of your day and a good weekend, that you're able to rest and recharge for next week and the week after. We're getting close to the end, as crazy as it sounds, which I'm sure some of you are looking forward to and some of you may be dreading. But take care, guys. I will be on office hours here in about 10 minutes. So if you have homework questions, feel free to swing on by.
Thank you.
Dr. Lopez.
All right, take care, guys.